Welcome. This presentation is about unknown input and stack estimation for linear systems. So let us consider a linear system with unknown input. And we have here x of t is of dimension n. It's in the stack vector. Y of t is of dimension p, where p is bigger than 1. And this is the output measurement vector. And d of t is an unknown input. In this presentation, for the sake of simplicity, we assume that dt is just one single unknown input. It can be a vector as well, and it does not cause any difficulty in the analysis at all. So in this model, we got matrix A is a square matrix of dimension n by n. C is the output matrix of dimension p by n. And because D of t is just a single input, so matrix D is a column matrix and it should be non-zero. So when we look at this model that represent the output measurement vector and the unknown input, we can see that they are linked through this stack vector. And this stack vector x of t is linked to the unknown input by this equation. And the output measurement vector is linked to the stack vector by this equation. So y of t is a linear combination of the stack vector. P is often less than n. In this presentation, we also do not consider the non-control input vector ut coming into the system. It does not cause any difficulty at all as far as observer design is concerned. So what we like to do, we would like to consider the following problem. We like to design an unknown input observer to asymptotically estimate the unknown input d of t. So you can see that the key word here is asymptotically. So we take the output measurement vector, we feed it into an unknown input observer, and then the output of that gives us the estimation of the unknown input in such a way that this estimation is asymptotically approaching the actual unknown input as time goes to infinity. So that's what we meant by asymptotically. Now, this is a classical problem, and in the literature, there are many methods considering the problem of estimation of unknown input. I would like to discuss a method by Hou and Muller. Hou and Muller. They propose a method for estimating, design an observer, a stack observer, to estimate the entire stack vector of linear system with unknown input. And as a byproduct of the method, the unknown input can also be estimated as well. Now, the sense of the method is based on a stack transformation. So what happened is they introduce a stack transformation matrix. Let's call it T, where T is a square n by n invertible matrix. So rank of T is n. And this relationship between the original vector and the new vector, which we call x bar t, is linked by this stack transformation matrix. According to Hou and Muller, matrix E is an arbitrary matrix of full column rank. It should be chosen in such a way that matrix T is invertible. In this composition, D is the input matrix came from equation 1 here. Okay, so because D is a column matrix, so E is of dimension n by n minus 1. So bear in mind that this is an arbitrary matrix of full column rank. It's chosen in such a way that T is invertible. Now, the significant feature of this transformation matrix is that when we take the inverse of T and we multiply by D, it gives us this special form. It gives us a zero column here of n minus 1 and an entry 1 in here. So that will be very useful. Later on, we will see that when we do the decomposition, we can actually get rid of an unknown input in one of the subvector. We can show that easily by simply multiplying both sides by t and t here. So if we multiply the left-hand side by a metric t, we can see that that gives us an identity matrix, and therefore the left-hand side gives us d. Similarly, the right-hand side, by substituting t equal to ed back into the expression and multiply by that special structure, we also obtain d as well. So this transformation matrix, as long as it's invertible, it gives us this desirable feature, special form there. Now, in the new stack vector x bar t, we partition it into two vectors. The first one is x1 bar, and x1 bar is of dimension n minus 1. And therefore, x2 bar is just a single variable. Furthermore, by defining a metric A bar, which is T inverse IT, and if we partition it according to the following submatrices, we can then substitute this transformation metric T into the original equation. And if we do that, we obtain the following equations. All right, now this can be easily done, and this is how it is done. So we basically have the original equation, and then by introducing this transformation, we replace x of t by t x bar, and therefore we obtain this expression here. And if we take the inverse, multiply both sides by the inverse of t, we will have t inverse it and t inverse d. And then by letting a bar and by partition it according to this form, we obtain this expression. Now, the significance of this inverse t times d is that we got this special structure. And as a result, we can express x1 bar, which is free of the unknown input. Okay, so that's where we got it in this form. So when we look at this equation, the significance of it is that it no longer contains the unknown input. It would be very nice if we can somehow express x2 bar in terms of the output measurement and this vector x1 bar. If that can be done, then we can see that we have a completely reduced order disturbance-free system. And that's exactly what we're going to do next. Okay, so we're going to focus on this equation. And according to Hou and Muller, this assumption is basically the product of matrix CD, matrix C times D. Know that it is actually a column matrix, And if it's non-zero, then what that means is it's actually equivalent to the observer matching condition. The general observer matching condition required the rank of CD equal to the rank of D, where D is a metric of more than one column. Now, if we focus on this equation, and if the assumption here holds, which basically matrix C times D should be non-zero. If that assumption holds, then Hou and Muller introduce an invertible matrix, which we call V here. V is a square matrix of dimension P by P. Now remember, P is the number of output measurements in this model here, okay? So if we consider a matrix V, which is invertible, square invertible, of course, and if V takes the following form, where we got C times D, C times D is matrix C times matrix D. This is a column, a single column, and therefore matrix P here is a column matrix with dimension P by P minus 1. According to Hou and Muller, at the moment, we basically assuming that P is an arbitrary matrix. It's an arbitrary matrix, and its full column rank, it should be chosen in such a way that V is invertible. Okay, so that's the only requirement. We pick a metric P according to Hou and Muller in such a way that metric V is invertible. If V is invertible, they further define the inverse of V, and they call it V1, V2, where V1 is just a row matrix, and V2 is of dimension P minus 1 by P. So we stack V1, V2 together. It's a square matrix, and V1, V2 is the inverse of the metric V. Now, if we have a look at V inverse times V, it should be identity matrix, yeah, which is the one given here. Now, by multiplying V1, V2 with CD and P, we obtain those submatrices there. So we can see that V1 CD is 1. So we got that expression there. And similarly, when we look at V2 CD, it should be 0. Should be 0 of dimension P minus 1. All right. So bear in mind that that's exactly what happening. So Hou and Muller make the assumption that if the observer matching condition is satisfied, in this particular situation, we have the matrix CD, which is a column matrix. It should be non-zero. And if it's not the case, by pre-multiplying both sides of equation 2a by V inverse, we see V1, V2. So we have the following expression. So we look at that left-hand side, we got V1, V2 times Y of t. And then this term we multiply by V1, V2, which is that term there. And this term we multiply by V1, V2. And so from equation 3, we can see that we can extract out two equations from it. The first equation is V1 Y of t, which is the one given here. And the left-hand side, V1 Y t. The right-hand side would have this term in there. V1 CE X1 bar of t. And then V1 CD X2 bar of t, which is this term in here. Now, if we focus on this equation, and if we substitute the relationship we obtain from here back into that equation, we would have V1 CD, which is just equal to 1. Okay, so we can simplify it thanks to this identity equation here, expression here. So we will have, we can arrange this equation, and it's clear that from this equation we are able to express x2 bar in terms of the output measurement and the vector x1 bar. Okay, so this is useful. The reason why it's useful is because we now able to obtain a completely decoupled, disturbance, or unknown input free reduced order system. And this is only possible with the assumption that this condition hold. Okay. So if that condition hold, we obtain this expression. And then let's leave it for the time being, and we can consider the next equation from equation 3. The next equation would be V2 times Y equal to V2 CE x1 bar plus V2 CD, and which is what we have in here. All right. So that equation I highlight in there is the result of the second equation that we can extract from equation 3. Keep in mind that V2 times CD, which is that relationship there, is actually equal to 0. Actually equal to 0. That is a good thing, because what we have in here is just simply an output measurement, which is related to the output measurement vector y of t. And if we call it y bar, for example, so let's say y bar of t equal to V2 y of t. Y of t is the output measurement vector, and V2 is a known matrix, which is the one that we define in here. And of course, that means that y bar itself is also a measurement, a known measurement vector. And then if we define V2C and we call it C1 tilde, then we have this equation 5 here. It is the output measurement vector in terms of the reduced order vector x1 bar. All right. Now, so let us go back into equation 2a. Remember, in equation 2a, which is the one given in here, it is completely disturbance-free. We substitute x2 bar from this equation 4 into equation 2a. This is exactly what we do in here. We substitute equation 4 into equation 2a. So that term there is now replacing by equation 4. And then we rearrange it. And the good thing about the outcome resulting of that is we got a reduced order disturbance-free system. So we got this reduced order system of dimension n minus 1 in terms of x1 bar, and in terms of the known output measurement vector. And this measurement vector y bar of t is linked to the original output measurement vector y of t. So if we look at this equation, wow, it's just a disturbance-free system, or a non-input free system. And certainly with this reduced order system, we can easily design a reduced order Lundberger observer to estimate x1 bar of t. Now this is achievable if the pair, the metric pair A1 tilde and C1 tilde is observable, which can be easily checked. By the way, there's a method for an equivalent expression for observable. We don't need to go deeply into that. But what happened in here is we got this metric A1 tilde is a known matrix. It's in terms of those sub-matrices, A1 1 bar, A bar 1, 2, V1, and E. So A1 tilde is a known matrix, and similarly, C1 tilde is also a known matrix, we see in terms of V2 and the metric E. So if we have this pair observable, and of course, we can certainly design an reduced order observer to estimate x1 bar. All right, now if we can estimate x1 bar, then from this equation in here, we can also estimate x2 bar, and that is given by this expression. Okay, so that means that the entire stack vector x bar t is known, can be estimated. And that entire stack vector is represented by x1 bar hat and x2 bar hat. And therefore, if we are interested in estimating the entire stack vector for the system, which is this x of t here, then it can be done. And it can be done in such a very simple and easy way. So we basically obtain a disturbance-free reduced order system. And if the pair is observable, we estimate this reduced order stack vector x1 bar. And based on that, we can reconstruct x2 bar hat. And as a result, the entire stack vector x bar t can be estimated. And as a result, the stack vector can be obtained. So this is based on Hou and Muller method. It's a very elegant way. It involves the stack transformation matrix T. It involves the assumption, the observer matching condition, and it's enable us to express this x2 bar in terms of the other output measurement and the reduced order stack vector. And so the entire stack vector of the system can be estimated. Now, let us go to look at how can we estimate the unknown input. That is our primary objective. So if we go back and we look at equation 2b, we see the one in here. We can rearrange and we can express the unknown input onto the left-hand side and then the rest of them onto the right-hand side. And that's where we obtain this equation here. Now, when we look at this equation, we know what is x2 bar in terms of the output measurement and the reduced order vector x1 bar. We can also take the differentiation of both sides with respect to time. And if we do that, we obtain the following expression. We also know how is x1 bar dot, which is the one given here, and that came from a reduced order disturbance-free system. You see the one in here, okay? So it's just a matter of routine substitution in, and we would be able to express x2 bar dot in terms of the first derivative of the output measurement vector, and the reduced order disturbance-free system x1 bar. Okay, so we will substitute that equation 9 back into equation 8, and we also replacing x2 bar by this expression. Then we obtain the unknown input d of t in its entirety. What it meant in here is, oh, the unknown input itself is related to the derivative. Now have a look at that term. It's basically v1 times y dot of t. So first derivative of the output measurement is required in here. And then the output measurement y of t, and then if we the entire term in here, we can simplify by calling that equal to Q2 is a matrix. It's actually a row matrix because D is just a single unknown input. This term here is also a row, we call it Q1. So in general, in summary, we obtain the unknown input expressed in terms of the output measurement. It's a first derivative of output measurement, and it's also linked to the stack vector of the reduced order disturbance-free system. All right. Now, so what we can do is we say, okay, according to Hou and Muller, the unknown input can be estimated. Of course, it can be estimated if we estimate the vector x1 bar of t. All right. So that according to Hou and Muller, as a byproduct of the stack observer, the unknown input can also be estimated using the first derivative of the output measurement, and an observer that estimate the reduced order stack vector x1 bar of t. Now let us make the following remarks or observation. Now when we look at the matrix V1, it's a row matrix and it has p elements in there. Now what is V1? V1 itself is this submatrix of the inverse of matrix V. And what is V? V is a matrix which consists of CD and P. And what is P? P itself is an arbitrary matrix according to Hou and Muller. It is chosen arbitrarily as long as the matrix V is invertible. So when we look at matrix V1, potentially, if we don't choose the matrix P correctly or according to a certain formula, we might end up with V1 which has P elements. This is just an element. It could be non-zero. And if there are P elements which are non-zero, And when we multiply by the derivative of the output measurement, we might require up to P measurements. We might need to take first derivative of P measurement. Okay. Now, in terms of practicality of it, the less number of first derivative of the output measurements we use, the better. So that is something that we're going to discuss later on. And the other thing is, according to Hou and Muller, the way to estimate the unknown input is based on the design of a reduced order n minus p observer. Now that was done way back in the 1992. Now with the recent development on functional observers, we can see that instead of designing the stack vector x1 bar, instead we should design a linear functional, a scalar linear functional observer to estimate that function, and that will give us much more similar observer structure. That is something that we're going to discuss later on. So in summary, according to Hou and Muller, the way it's done is a very elegant metric decomposition method, a very elegant metric decomposition, very easy to follow. Here we just have a single unknown input. If it's more than, it shouldn't be any problem. So introduce the matrix transformation T, where T is ED, and at the moment E is an arbitrary matrix. As long as it is chosen in such a way that T is invertible, the transformation will decouple the unknown input completely from x1 bar, and so we obtain a reduced order system. And with this reduced order system, which is disturbance free, of course, we require the observer matching condition. If that holds true, we got this reduced order disturbance free systems. And with this system, we can, of course, do many things we like to do. For instance, estimate the entire stack vector x1 bar using a reduced order system of dimension n minus p. As a byproduct of the approach, the unknown input can be expressed in its entirety, which is involve the first derivative of the output measurement and the reduced order stack vector x1 bar. And if we want to estimate it, then it can be done as well. Okay, so that is essentially the essence of Hou and Muller method. And so thank you very much for watching. Now, please join me in the next video. In talk number 2, we will present a similar and more practical unknown input observer. So instead of design an observer to estimate the unknown input in this form, it could have up to derivatives of P measurements. We will make it less, maybe one measurement only, derivative of one measurement only. And instead of design an observer to estimate the entire stack vector of x1 bar, we will design a scalar functional observer. Okay, so that's what we're going to do next. And so we will reduce the complexity of the current design method by Hou and Muller. So thank you very much, everyone, for watching. And I will see you later in the next talk. Bye.